So we've learned about aluminium, what it does. Now somebody came along and said, we'd like to coat that. We'd like to electroplate it. So we're going to have a quick resume of what aluminium is and why is it different to plate from some of the other conventional metals such as steel, brass and copper. So you've seen already the aluminium properties: atomic mass, silvery white, non-magnetic. You've heard all this before. Density, when it was discovered, melting point, good electrical properties. Alloying, such as magnesium, manganese, silicon, copper, to name but a few. So again, it was soon recognised that aluminium contains superior properties. Power transmission lines, electrical wiring for railways, early use in engines, the Wright brothers' first biplane, as we mentioned before. Aluminium foil entered the market in 1910, and the alloy development began in 1911 to improve its physical properties. And by the way, me and Jan have not been together, it's just coincidental that we've ended up with a similar beginning. So as the technology of aluminium was increased, so it was that industry decided it'd be beneficial perhaps to plate it. Somebody said, well, we've got this wonderful material, why can't we cover it with something else? So the idea was to enhance its appearance, make it look pretty, increase its corrosion resistance, as if it hasn't already got good corrosion resistance. And you can use a lower-based metal, such as aluminium, instead of copper or brass, and coat that and get the same sort of result. So, a little bit of chemistry. No, don't touch it. All elements like to increase into their lowest energy state, and we're going into what is the electrochemical series. So, a little bit of chemistry. It's built up by arranging various redox equilibria. So you get standard electrode potentials. You put a metal into a solution, it has a potential. And if you connect that to a standard electrode, such as hydrogen, which has 0 voltage, every other metal will have either a more negative voltage or a more positive voltage with respect to hydrogen. Okay? That's it. And you end up with the electrochemical series. And here you have hydrogen, which they assume is 0 volts. So if you dip a piece of copper and connect the two together, it's a battery basically. But the copper will have a positive voltage compared to the hydrogen, silver, gold, as you go down. So these metals actually become more noble compared to hydrogen. So they have a less affinity for oxygen, which is what Jan was saying. Now, as you go up, lead, iron, zinc, aluminium, magnesium, they have a greater affinity for oxygen, and they have a negative potential with respect to hydrogen. So the more negative this becomes, the more reactive the material becomes with oxygen. I'm sure we've all been at school and we've probably seen the little bit of sodium that's placed on water and it darts around, potassium as well, nice lilac flame, and again, it's all down to this fact that these materials just love oxygen. They'll grab it wherever they can. And aluminium, if you click it once more, aluminium is the one that we're talking about here. If you look at aluminium and you look at iron, aluminium will always have this oxide film on. But if you take a piece of pure iron and just leave it in a room, it will look like a grey metal. Only when there's humidity around will it start to corrode, rust. So because this is a much lower potential, quite a bit lower actually, minus 1.2 volts, the reaction with oxygen is a lot slower with iron than it is with aluminium. Now, the wonderful thing about aluminium, because aluminium oxide is stable, it'll all stay together. It doesn't fall to bits. Iron rusts, and we all know the outcome of rust. It just falls apart as the dust on the floor eventually. So it's not a stable product. Okay? So what are we looking at the surface of the aluminium? Okay. And again. So if you imagine that's a piece of aluminium, that nice piece of grey, greyish white, depends what you've got in your hands, but that's aluminium. Okay. So we'll stick our magnifying glass over it, and we'll see actually what we're looking at is this oxide layer. But it looks like metal to us, but as Jan was saying, it is the oxide layer. Okay, so we've got this oxide layer here, and the formula that happens is 2 aluminiums react with 3 oxygens to produce aluminium oxide, which is this layer you're looking at. So when you've got your piece of aluminium, and I do have a sample of a piece of aluminium. That's just polished aluminium. What you're looking at actually is the oxide layer, but it just looks like metal. That's just a piece of polished standard aluminium. Okay? So why can't we plate on there? You can plate on there. You can connect that up, you can stick it into a plating tank, clean it, stick it into a plating tank, and you get a beautiful coating on it. Look lovely. Till you file the edge off and it rolls off and falls off. Because what it's trying to stick to is the oxide layer, not the metal underneath. Okay? So again, going back to the electrochemical series, if you look at copper, copper remains copper. It doesn't become an oxide. So you can stick to that. Once you've cleaned it, activate it with a little bit of acid, made it nice and clean, dip it in your plating tank. You can nickel plate it, you can copper plate it, you can silver plate it, etc., and it will stick. Okay? Iron's exactly the same. Provided it's not rusty and you've got rid of the rust, immediately electroplate it, it bonds. No problem. Aluminium, obviously, is a different story because you've got this oxide layer. And the same would go for magnesium as well. Magnesium can be plated. It's even more difficult than aluminium because its affinity to oxygen is even greater than it was with aluminium. So we include that it has a strong affinity for oxygen. You plate directly on the oxide layer. If you do that, it won't stick, just give you bad adhesion. So we need to remove the oxide layer. That is an absolute must. And when you've removed that oxide layer during the chemical process, you don't want it reforming again. So how do we prepare the aluminium for plating and its alloys for electroplating? So the first part is degreasing. Okay. So you've got your piece of aluminium, not necessarily a flat sheet, that's only for demonstration. So you've got whatever it is you want to place. It's been machined, it's been filed, it's been everything. It might be covered absolutely with oils, greases and everything else. And we all know that in electroplating you can't stick to greasy surfaces. Okay, so you've got to degrease it. So what you do is you generally soak the parts in a water-based neutral pH cleaner. It has to be neutral pH because aluminium is amphoteric. Any strong acid it will dissolve in, any strong alkali it will dissolve in. There's not much point in cleaning it in a strong caustic solution because especially if you've got to maintain tolerances, because when you get it out the tank it's probably half the size than when you started in the first place. So you use a neutral pH round about 6.5, 7.5. Lots of surfactants in it, wetting agents, lots of emulsifiers to get the oil to soak into the cleaner off the part. And there's commercial products around, not going into any names, but these are normally just powders made up between 50 and 100 grams per litre, temperatures 50 to 70 degrees centigrade, and immersion times 5 to 15 minutes. It doesn't really matter, it depends on how heavy the grease is. One thing that if you look at steels, for example, steels in chemical cleaners use very high alkalinity solutions. And also they pass electricity through them to make them fizz. And as they fizz, all the grease comes off. You tend not to do that with aluminium. It tends to be really a soak process. And if you want to cause some disturbance, they use ultrasonics to clean it. Okay? So then you rinse it in running cold water. And this part is the part really that's important in any electroplating process. You must make sure that there's no what I call duck's back effect. The water does not go into globules and run off. If it goes into globules and run off, it ain't clean. It's got grease on it. It should hang in water. And that's one thing, if you're doing manual electroplating of aluminium, you can go through the processes and look at the part. If it's running off, you've got a problem. You've really got to go back a stage, make sure that that is water break free, otherwise that part will not stick in the electroplating process. So we've cleaned it, nice clean surface. Now we've got to get the stuff to stick to it, so we've got to key the surface, produce some sort of roughening of the aluminium. A little bit like painting. Before you put your primer down, use a bit of sandpaper to rub the wood down, gives you that keying effect. The alloys provide strength and rigidity to soft aluminium and therefore increase in usage. So these are the metals that you have. So there's magnesium, manganese, copper, silicon as well as we've been measured. Remember that all these could be in the alloy when you etch the surface of the thing. Okay? So as I mentioned before, it's amphoteric. So it's affinity for both acid and alkaline chemistry and will react to both. The problem is, if you've got an alloy, if you've got pure aluminium and you put it in caustic soda, sodium hydroxide, it will dissolve, it will fizz, it will gas, beautiful. If it's got an alloy with it, the other metals that are in the surface may not react quite the same way as the aluminium. So if you've got, for example, copper in it, you'll etch the aluminium away from the copper will just sit there because, remember, it's not got the affinity for oxygen, it's quite happy to stay as copper. So you tend to get selective etching on the surface if you use an alkaline cleaner. Okay? So the types of etch that we use are alkaline etches, which are primarily sodium hydroxide based, and they're used between 30 and 60 degrees C. And as I've said, the other metals in the alloy will react with acids or alkalis differently and can lead to a smut on the surface. Now, if we take copper and aluminium, the aluminium dissolves beautifully. It'll be left with a nice white aluminium, look lovely. The copper, unfortunately, reacts with the caustic to form copper oxide, which is black. So some products that have a lot of copper in, when you've etched them alkaline etches, when you take them out, they've gone from a lovely white to a deep black colour. Also, if you use an alkaline etch, aluminium hydroxide is insoluble. So eventually you end up with a sludge all in the bottom of the tank, and it gets deeper and deeper and deeper and deeper. And you have to empty it out and clean it out, but it's just a fact of life. There isn't much you can do about it. Okay? So let's look at the effect of copper in the alloy. It tends not to dissolve, but it produces this predominantly black colour, and it seriously can be black. I mean, it can be as black as that. Completely jet black. In fact, if you go into the printed circuit board industry, they deliberately produce black copper oxide so they can stick boards together. It's got a lattice on it, and it can anchor glues and things like that and stick together. Not very good for electroplating though, unfortunately.